So now we will discuss a problem on the stiffness method. We have a fixed ended beam, a double fixed beam with left side support A and right side C. We know that there won't be any vertical, horizontal, and rotation at A and C. And due to the loading, there can be a rotation at B. So it can like this. There won't be rotation and deflections at A I have already explained, and about B can be like this. Okay, so this is this value, this theta B, if you would note, it will be equal on left and right, and that is something unknown parameter or unknown degrees of freedom. So for this question, with the AC beam with midpoint as B, it is hinge support, and with the loading 24 and 12 at the midpoints of respective AB and BC, and having total length of 10 plus 10 20 meter, the kinematic indeterminacy is equal to 1, which is the rotation at the beam. Okay, so this is the degrees of freedom we have marked with respect to the joint displacement, that is the dj1. It's the first indeterminacy. The member stiffness matrix of the beam member is equal to SMI is equal to 2EI by L into 2112. So we have already discussed and derived the member stiffness matrix of the beam member in the previous slides. Yeah, we have it here. The member stiffness matrix 2EI by L into 2112. And the unassembled stiffness matrix will be, we have two beams AB and BC. So the AB parameters will come in the first phase, and the BC parameters will come in the second phase. Okay, so 2 and 10 get cancelled, so EA by 5 will come, and so EA by 5 into, this is for AB and this is for BC, and this will be the unassembled stiffness matrix SM. Then we are making this beam as two individually fixed beams, that is, yeah, like this. So this AB is here. Let this be AB and this be BC. We're going to make the both ends fixed. Similarly for AB and for BC, and with the point load 24 for AB and with the point load 12. So we know the moment value as well as the reaction value. The moment value will be WL by 8 for both left and right supports, and for here also it will be WL by 8, and the reaction will be W by 2. So the values WL by 8 are written here for AB. Similarly for the loading, 12 WL by 8 is 15, and the reaction will be half the vertical load, which are not here, which will be the fixed end action. And the equivalent joint load, as we have discussed, it will be the negative of the a fixed reaction. So this being a anti-clockwise moment, you should apply a clockwise moment, and all the reaction should be negative. It is actually in the fixed was upward. This is actually 12 plus 6 upwards, 6 upwards. So all will be downwards in the equivalent joint load, and the net effect bending moment will be, this is at 30 clockwise and this is 15 anti-clockwise. So 15 clockwise will be the fixed one, and the 15 anti-clockwise will be the equivalent joint load. Now we are going to find the displacement transformation matrix CMG, which we have discussed in the previous slide. We had displacement transformation matrix. The displacement transformation matrix mainly it relates the member displacement to the structure displacement. This is actually the CMS, which is the displacement transformation matrix. So in the stiffness method, you will be applying a unit deformation, and you are supposed to find the reaction which is required to make the unit rotation. Okay, here is such a rotation because there is a change in angle there is no displacement in the vertical as well as the horizontal directions. So on the application of this one, the values will be 0 here, 1 here, 1 here, 1 here. So the rotations will be 1 at this point and 1 at this point, and being 0 at left and right support. So the CMJ will be 0, 1, 1, 0, and DJ1 is equal to 1 due to the joint. Then we have to use the set of equations which we have discussed in the previous slide. These important formulas are there. We want to by heart this formula or to relate these formulas and then solve for the joint displacement, support reaction, as well as the member end reactions. So actions. So we know the equation dj is equal to sjj inverse into aj. The complete equation is dj is equal to sjj inverse into aj minus sjr into dr. So this term is not there, hence being the displacement due to the redundant is actually a null matrix. So dj is equal to sjj inverse into aj, and we know that sjj is equal to cmj transpose into sm into cmj, which we have discussed also. Sjj is equal to this equation. So sjj is equal to cmj transpose into sm into cmj. So we know the cmj value, we know the dj value, and cmj transpose, it was initially a column matrix, so transposing it to a row matrix. Then sm, we have discussed unassembled stiffness, unassembled stiffness matrix sm is multiplied with that one, and then again the column matrix will give you 4a by 5 as the sjj, and the joint displacement is equal to we have the equation dj is equal to sjj inverse into aj. So the aj is equal is the fixed or the moment acting at the joint b, hence the inverse of this one, inverse of the sjj will be 5 by 4a into, then into aj will be there, the AJ will give you 15 and the value will be 18.75 by EI will be the rotation at the point B, which will be equal both at the left side and the right side. So we found the first one, joint displacement. Okay, then after getting the joint displacement, we can proceed to the support reaction and the member end actions. Okay, so after finding the differential shape, we have the member and action equation. Then AM final is equal to AMF plus SM into CMJ into DJ. Yeah. So we have those equation as the last one. So the member and action is equal to AM final is equal to AMF plus SM into CMJ into DJ. And note one more thing, SM CMJ DJ. SM CMJ DJ are there. We know that DR is a null matrix. That is, there is no displacement at the redundant. Hence, that last term will go to 0. Hence, we have the AM final is equal to AMF plus SM into CMJ DJ. So AM final is equal to AMF is the member force. So yeah, so this is the from this one we found the member loads, which is 30 anti-clockwise taken as positive, then clockwise is negative, so 30 minus 30, then this is also anti-clockwise, so positive, clockwise is negative, will be the a member force plus EI by 5. We have this value as a SM value. Yeah, SM is EI by 5 into this unassembled matrix. Then into CMJ, we have the value CMJ into the AJ will be there. Sorry, into DJ will be there, which we have found from the previous slide, 18.75 by EI. So multiplying all those things will give you the AM final value, which is equal to 33.75 minus 22.5, 22.5 and 11.25. And to find the member reactions, that's especially we need to find the RB. We're considering all the loads happening to the beam. So we have for the beam AB, we have 24 kilonewton at the midspan, 12 at the midspan for BC, and also the finalized moments are finalized action moments are 33.75 minus 22.5, 22.5 and minus 11.25. So those are marked accordingly. That is, this is actually positive, so being anti-clockwise. So anti-clockwise, and the next one is minus 22.5, which will be the clockwise. 22.5, it will be the anti-clockwise, and last one will be anti-clockwise with the usual loads. So this will be the final one. So taking the condition sigma moment at the B is equal to 0, we have Ra into 10 minus 33.75, because this Ra into 10 will be the clockwise moment, so hereditary against positive, then minus 33.75 being anti-clockwise. Actually, there is no, if you should follow a single sign, that is, if you're taking anti-clockwise positive, then all should be in that way, otherwise it should be clockwise. So we are taking an equation with a defined sign. Okay, so R in 10 is actually clockwise, minus 33.75 is anti-clockwise, then this 24 into 5 will be again anti-clockwise, so minus will give you the resultant moment at the point B is 32.5. Hence, RA is equal to 13.125 and B1. So we know total value of 24 is which is acting downwards. So 24 minus 13.125 will give you 10.875. Similarly, taking the moment with respect to C, we have the resultant moment is equal to 11.25. Follow the same conventions. RB2 into 10 will be taken as positive, clockwise positive, minus 22.5 being anti-clockwise, minus 12 into 5 being anti-clockwise, equal to, this is also equal to minus 11.25 being on the other side of the equation. So RB2 is equal to 7.125 kilonewton. RC is equal to total load is 12 minus 7.125 will give you 4.875 kilonewton. The total reaction RB is equal to RB1 plus RB2 is equal to 18 kilonewton. Okay, then writing all the member and moments from the previous slides, like from here, the member and moments are written here: 33.75, 24, 12, 22.25, 11.25, and the minimum diagram is also found considering the 24 kilonewton and the 12 kilonewton. The problem 2, the question is to analyze a fixed beam of a length total 8 meter, 4 meter, 4 meter equidistant, and here there is no support to the beam, but B is at point B there is a point load acting, and also a moment is acting, and also on the left side UDL is acting 9 kilonewton per meter, and the forces are 20 as well as 40. Okay, and note that for this beam it is 2 EI, and for the right beam it is EI. So the total kinematic indeterminacy will be the vertical deflection. It is the beam will bend like this on the action of the load. The beam will have Yeah. So it will be at this point. Actually, there is some error in this one. It should actually happen at exactly at the having a fixed here. This is exactly here, so that it will be rotation as well as the displacement also. So the kinematic indeterminacy is equal to 2, the rotation and the deflection at the B, considering the B as a node. The member stiffness matrix for the B member, we have already discussed, that is SMI is equal to 2A by L into 2 1 1 2, and the unassembled stiffness matrix SM is equal to 2EA by L into the, this is actually for the beam portion AB and this is for the beam portion BC. And in similar way, we are finding the fixed end moments. So for the UDL, we have WL square by 12, and for the right side, we don't have any loading. This load is actually exactly on the B, and this moment is also on the B. So only we need to convert the UDL to the equivalent joint load. So the left side there will be the moment as well as the reaction, and for the right side there is no contribution from the loads acting other than the joint. Hence, the equivalent joint load will be adding the combined joint load will be equivalent joint load plus the actual joint load. So the reverse of the previous load is applied, 12 kilonewton meter, then 18 kilonewton in the reverse direction. Then the actual load is 12 plus 40, because 12 is the moment acting here and 40 is the actual moment acting at the point. And we have AJ2 is equal to 18 plus 20. 18 is the force here, and 12 20 is the load acting at the joint. So please note that for the previous problem, there were no exactly the joint load, because these loads which were acting were converted to the equivalent joint load. So that's why here for this one, but we have one actual load also to be added to the equivalent joint load, which is shown here. Okay. Then the next one, a CMJ formulation, because CMJ is also an important one. The displacement transformation matrix. The member consists of the member displacement due to the unit displacement on the restraint structure. So we know that for the point B there are rotation as well as the unit displacement. So we are writing the CMJ for individually for the rotation and the displacement. The dj1 will be the rotation one, and dj2 will be corresponding to the translation. So upon the action of or the rotation here, the theta is equal to 1. So here theta is equal to 0, theta equal to 0. So 0, 0, and here the value is 1 and 1. So it is represented, actually the value 1 by 4 is taken out for the calculation purpose. So in a way, when you directly multiply 1 by 4 into 0, 4 will be this actually 1, and 1 by 4 into 4 will be 1. So 0, 1, 1, 0 will be the first column. And for the second one, we have yeah. So for the second case, we are applying a unit displacement to the in the point of B here, and the corresponding deflections at the various points are noted as minus 1 by 4, 1 by minus 1 by 4, being both that's clockwise, and 1 by 4, 1 by 4 for the right support. So this is actually found by like this. So there is two support point A and B, and once one of the support is getting settled, then the corresponding rotation will be 1 by L for the both the sides. Okay, so minus 1 by 4, minus 1 by 4, and 1 by 4 and 1 by 4 for the right side. It is written at the dj2 column, minus 1, minus 1, 1 and 1. It's explained here. And also the displacement due to the redundants are found as displacement transfer displacement metrics due to the redundant CMR. So we have DR1, DR2, DR3 and DR4 correspond to the vertical deflection of 1 will be DR1, and DR2 will be the rotation of 1 unit. Then DR3 will be the vertical displacement to 1 unit, and DR4 will be the rotation to 1 unit. CMR is equal to, so the corresponding, because the settlement will be 1 by 4 and 1 by 4, and the corresponding moments will be 0 for the coordinate 3 and 4. Just a minute. Yeah. So when the deflection is applied to the point here A, and the corresponding deflections at point A, sorry, A, B, then for the B, C are written in this column. So for this like this, so when there is an support settlement here, then the 1 by 4, 1 by 4, it is 1 by L will be the corresponding rotation, and it won't affect the second BC element, so 0 0. And for the DR2 is equal to 1, that is applying a unit moment here, only here there will be rotation. Okay, so only this is noted as 1 here. As remember A, this is for the A, this is A, this is B, then again B right side and C. Okay, so other two will be 0 0 0. Then for DR3 we have there is no deformation for AB, so A and B are 0. Then the BC will be minus 1 by 4, minus 1 by 4. So these angles, this values are based on the positive negative, it is based on the direction of the moments. And therefore we are applying a clockwise anti-clockwise rotation, so it will be like this, so it will be 1. And for all other member A, B, and for the B of the BC member, all will be 0. Hence the CMR matrix due to the redundant. Then the joint displacement, that is dj is equal to sjj inverse into Aj minus Sjr into Dr. Here there is no support displacement specified in the problem, hence Dr will be 0. So Dj is equal to Sjj inverse into Aj. Sjj we know when we tried for the previous problem, Cmj transpose into Sm into Cmj. So the values are directly applied and the resulting values are obtained. Therefore, the Dj from the Sjj inverse into Aj will give you 1 by Ei into 9.70 and minus 61.09. This the first one, 9.70 is the rotation, and 61.09 by A will be the vertical deflection. Then the member and action AM finally is equal to AMF plus SM into CMJ DJ plus CMR DR. We know that there is no support settlements or DR will be null matrix, so this term will get 0. So AMF plus SM into CMJ into DJ is equal to 12 minus 12 0 plus 2 EA by L into 4200, which we have the SM matrix into CMJ into DJ will give you the member and actions. So finally the member and action, the action will be 67.52, 53.22, 13.21 and 18.06 with the necessary signs. And the moments are written as like this: 67.52, 13.21, 53.22 and 18.06, drawing to a BMD diagram with the necessary signs give you the BMD. And also the support reaction AR is equal to minus ARC plus SRJ into DJ plus SRR into DR. We know DR is a null matrix, so this will be equal to 0. And SRJ is equal to CMR transpose into SM into CMJ. So this is we found before 2 slides CMR value into SM into CMJ will give you the SRJ value. Then this SRJ into DJ, which we have find from the previous slide. DJ ARC plus SRJ and DJ will give you the final redundant reaction, support reaction 48.18, 67.52, 7.82 and 18.06 as a solution. That's all for today. Thank you.